So basically, now that you are asking about machine learning, it can also connect a bit with what I did in my research, and I think I will also give some more inputs about how the HAN operates, in this case more about the base station. So usually, as I told you, we have a base station is where the antennas are, and it's basically it manages the interface with the user.
Yeah.
Okay. And typically, the base stations in current networks are deployed in a 3-sector manner. Okay. We have 3 sectors. Okay. This is a base station. We have 3 sectors. Basically, 3 sectors is
120 degrees phases.
Yeah. You can basically consider that. Let's do it this way. Okay. So you have 1 sector for each 120 degrees.
Okay.
Okay, and in each of these sectors we can have 1 antenna or a multiple antenna system. Okay?
Yeah.
So basically it's where the antennas. And this was when the network was initially deployed, or the first antenna systems were based on omnidirectional antennas. Okay.
Yeah.
But then this has some disadvantages about coverage interference, because if you have another neighboring base station, we'll have this interference here. Okay.
Yeah.
With this architecture, we can, for example, deploy a neighboring base station here, for example, and we can plan it to cover the locations where the neighboring sector is less intense, which is here. Okay, in this frontier between sectors, we don't have much signal, so we point the neighboring sector center to that
So you aim
direction.
to avoid interference.
Yeah, so we can avoid interference. Because we are doing this sectorized manner, we can basically concentrate the energy towards that, towards that direction. So we concentrate all this energy towards one direction, which means that the signal can go farther from the base station when we have the 3 sectors, so we improve coverage as well. In addition, because we have 3 sectors, it is also very good in terms of capacity. Okay? Because in here, you basically have 1 antenna system radiating in all directions, so you will only have 1 BBU or RRU. In here, you can have 3, 1 per sector, so you increase a lot the capacity. And you also increase the spectral efficiency with 3 sectors, because you can use the same frequency in different sectors. Okay?
Yeah.
For example, like that. In here you can only use 1 frequency, so you have limited bandwidth. So you can have 3 times the bandwidth here than here. Yeah. So this is how base stations are deployed nowadays. So basically, this is how the base station is deployed nowadays, but still we continue to have some problems with this architecture, because when we have 3 sectors, we have more signal here. This is what we call like a beam.
Okay.
So this is how we tend to represent the coverage area of this sector. With the beam.
Yeah.
And we have still a lot of interference problems. Despite this being much better than the omnidirectional scenario, we still have a lot of interfering problems. Not only because basically we have a lot of base stations in our networks nowadays, so this raises interference in general. So it's how we represent, so the beams is how we represent the coverage of each sector in cellular systems. But we still have, despite the omnidirectional, despite the 3 sectors being much better than the omnidirectional in terms of interference, we still have some issues. One of the main causes is because we have so many base stations in our networks that the interference just simply raises a lot.
Like with 5G, you want to use even more base stations, right?
Yeah,
because you want to you want to go millimeter wave.
Exactly.
And as we discussed, that requires line of sight.
Yeah.
So that means you have to have base station every 10 meters or so.
It's very
it's very dense.
Very dense, yeah. And this fact leads to a very common problem since the first iterations of cellular networks, which is the cell edge problem. The cell edge problem is, I will draw another base station here. Yeah, the cell edge problem is basically the frontier between sectors of the same site or different sites. Okay, so let's say that we have a user here, and he's being served by this beam here, and then it starts move to the other sector.
Okay.
Okay, in this area, for example, in the middle of sectors, usually the beams are a bit larger than this, but still in this frontier here of the sectors.
Yeah.
Okay, this is typically characterized by high interference. Okay, because you have signaling coming from the two sectors,
Right. Okay.
and because the user is not, so we always have interference in any place, but here because the user is clearly being covered by this beam, the received power is much higher than what comes from the interferers, so the quality of the signal is good. When you move to edge of the cell or edge of the sector, we can still have some decent received power, but the strength of the neighboring signal is also much higher, so the quality of the signal decreases. So
Right.
this is what we call the cell edge problem. So is these locations in the frontier? It can be between sectors of the same site. It can also be between sectors of different sites when the user moves from here to this.
Okay.
Yeah. So we have this interference, we call it the cell edge. We can also define the cell edge simply as the coverage, as the maximum coverage of each cell. So for example, this does not happen typically in urban scenarios because we have a lot of base stations, but for example in a rural area, we can go so far away from a base station that you just simply lose signal because you are too far away from the base station.
Of course.
Okay, so yeah, that's the frontier. Maybe you can call cell edge to like the frontier of the coverage of a sector, but typically when we call cell edge problem is related to this interference situation. Okay, so basically the idea that I have been studying during my PhD is to try to solve this cell edge problem, because it is anticipated that the cell edge problem is going to be even worse when we start to go to 5G, where we want this massive densification of base stations. Even if sometimes using millimeter waves, sometimes we may not use millimeter waves, but we will have much more interference.
Yeah.
And it's true that typically when we deploy more base stations, they have shorter cell radius, because or we increase the frequency, or we tend to, for example, do you know what tilt is?
I do,
Okay.
but my watchers probably
No?
won't.
Okay. So when we have an antenna, let me
Yeah.
draw it here. Let's say this is the antenna, okay? It transmits signal in this way. It has a tilt,
Yeah.
okay? So a tilt is what we call...
So it's like an angle.
It's the angle between... it's the angle between the orientation of the signal transmission and the vertical axis.
Okay.
This is the tilt. Okay. Usually, if you don't want the signal to spread too much, we just reduce the tilt and we
Okay.
downgrade the.
So that it looks downwards.
Yeah, it points downwards. Okay.
Yeah.
And this also allows to manage interference. When we do network planning, it's very important that we define a proper tilt so the signal doesn't spread all over the place and interferes with neighboring base stations.
Yeah, makes sense. And how does that relate to
Yeah.
cell edge?
Exactly. What I was saying is, when we deploy massive base stations, we can play with the tilt, we can play with the frequency, but it's not linear. Okay, the variation is not linear. Because why? Because we go back to run again. If we have a base station here and the user here, okay, the signal that goes from the base station to the user suffers multiple kinds of attenuation in this path.
Yeah.
Okay. Basically, this is the air interface that I mentioned before between the user and the base station, and we have a lot of attenuation of the signal. First of all, because of the distance. Okay, what we call path loss.
Yes.
Okay, path loss is basically depends on the distance from the base station to the user, and then there's what we call fading. Okay.
Yeah.
Fading is there are two types of fading. the large-scale fading or small-scale fading. Usually, large-scale fading is defined by the attenuation of the signal that is caused due to buildings
due to
or
reflections,
elevation, stuff like that.
Basically, physical properties of the environment.
Exactly. And when we have small-scale fading, is basically signal attenuation that is caused. So it's fast variation of the signal attenuation. Okay. So you can be in a place and you are on the phone, but then you have a car that moves in front of you, so there's a change in the signal, but then it goes back to normal. So small-scale fading is also called fast fading, and it is characterized by these fast variations in the signal that could be related to many things. You can change your position, we get with more interference, with different signal.
Yeah, with millimeter wave, you can simply have a hand like
exactly
in front of the base station, and that's enough to change
it will mess up with the signal and the change. But you can be with very good signal in 1 second, in the next second be with very bad. So it's like this very big change. And so this is the kind of attenuation that we face when in this path between the user and the base station.
For instance, in rural areas, you can have satellite internet sometimes and like things like that, which can improve the quality of your signal or give you some signal. But how else can you solve this problem other than just building more base stations?
Yeah, because I was saying that with the amount of base stations, I was justifying why the amount of base stations also interferes with the cell edge. And I was saying that the fact that even when we increase the number of base stations, we play with the frequency, we play with the tilt, so we have lower ranges of the cell. But because there's these attenuations that I just explained, so the fact that you reduce the cell range, it doesn't mean that you proportionally reduce the interference. Because you have these variations in the signal that many times they are classified as random. So you can play with the tilt, you can do a study for the cell range, but you still have a lot of random reflections of the signal that will reach other place anyways. So you still have a lot of interference. So this is why we need to think about alternatives to fight this increase in interference. And even it might be by not deploying so many base stations. So what I've been working on is in a cell sweeping system. Okay. The idea of cell sweeping is, as I told you in my examples, we have this 3-sector architecture, typical architecture, which causes interference in the frontiers between sectors. Okay. The idea with cell sweeping is basically sweep the cells. Instead of keep the cells or the sectors static, the sectors can rotate or sweep in time. Okay, they basically do this movement. So let's say in instant, this is in instant one.
So basically your base stations do angular rotations.
In the azimuth. So the azimuth is the angle between the sector direction and the geographic north. And basically we keep changing this azimuth. So for example, in one instant we have this direction of the sectors, in the next instant we can have something like this.
So, and this is a smart environment. What's the input? How is it?
So the initial idea of cell sweeping is that it is simply you are designing it as a new way of deploying base stations. It doesn't need to have any smart features at the moment. We just think that the fact that we keep the cells sweeping instead of keeping them static will improve the network by itself. And And of course we need to adapt some of other existing mechanisms to be able.
But don't you need like to sync them together?
This is one of the so you mean synchronizing the sector, the sweeping between different base stations,
so that they don't start causing interference.
Of course. This is part of the planning.
But doesn't it make it smart in that case?
I wouldn't. I think it's basically network planning. Okay.
It's just network
Yeah,
planning.
because with cell sweeping, we can define the sweeping speed. So we can define basically two main parameters: p for period of sweeping or rotation, and a for the amplitude. Okay. So if p is equal to 1 second and a is equal to 30 degrees, this means that the sectors will sweep 30 degrees every second.
Okay.
Okay, so you have this. So, and the idea is that, okay, we configure these parameters when we deploy the base station, depending on the environment and on the neighbors, because this is all. So we don't need them to, this kind of configuration, we don't need it to be smart, because we can just, when we do the radio network planning, we can just define these configuration parameters. Okay, and the idea, the main idea of cell sweeping is that we can, instead of having these frontiers, let's say that we have a user in this frontier here that I drew before. Okay, so he is in a bad situation.
Yeah.
He is getting a lot of interference. So the thing is, with sweeping the sectors, at some point this beam will point into his direction.
So it will change, yeah.
Yeah, so it means that even if a user is in a bad radio condition at one point, with cell sweeping it will be in very good conditions at a certain step in this rotation process.
Yes.
Okay, so basically we can mitigate. Basically, if you do the cell sweeping, you can actually completely mitigate this drop in the cell edge between sectors of the same site. And then if we coordinate this sweeping between different sites, we can also erase the cell edge between the sectors of different sites.
I see, yeah.
Okay, because if we, yeah, exactly. So this is the main idea. So we can decrease the cell edge problem, so this interference problem, because we are just serving the users when the beam is, center of the beam is pointing into that direction, and we are avoiding to serve users when they are in these frontier locations. Okay.
Okay.
Okay. Yeah. And for example, of course, if we have, I will erase this. So let's say that we have two sectors, one like this, from different base stations, and one like this.
Yeah.
Okay. If a user is in this place, so we will be in the frontier of the two sectors. Okay. So in here we can solve this, whether you use cell sweeping or static. So that's why I am saying synchronizing the movement between different sectors. So we, instead of this situation happening, we have something like this.
Okay, so it's pointing in a different direction.
Pointing in a different direction. Okay.
Yeah. Doesn't it mean that to coordinate all those base stations, they must be all made by the same operator or operated by the same company?
Yeah, okay. So in real networks, usually when we do network planning, we do it by operator.
Yeah.
So we configure the entire network of one operator. So that's how things work. So yeah, of course, if we want to do this, we need to have this coordination between all the base stations of that operator. But it doesn't limit you to have one operator. Okay.
Right.
Yeah. But yeah, and the same for the idea is, in terms of vendor, it should not impact the vendor, because that's why we are saying that we want this to be a new way of deploying base stations without changing much. Okay, and we think that that would be possible, and because when we say this, we mean that we don't want changes in the BBU. You remember the BBU from RUN,
yes,
which is proprietary of vendors.
Yeah.
So we don't want to change anything in the BBU. Maximum you can. This is simply a radio frequency, an RF system. So we might need to change something in the RRU, okay, but not in the BBU. So it doesn't. It means that we are not depending on each vendor. Okay. And yeah, so this is the main idea. There's some, of course, there's a lot behind this to explore. One of the things is that we are trying to not make it. We are trying to not make it a physical sweeping. Okay.
How do you mean, like you can do sweeping on software?
Electrical.
Electrical.
Yeah.
Why? In terms of receiving signal? Or,
No.
I don't understand.
Yeah, it's like you can electrically steer the beam.
Yeah.
Yeah, you can do it.
Why? By combining phases or
You can use phase shifters or...
by phase shifters?
Yeah, but the idea was not to use phase shifters. So one of the implementation ideas that we have, or yeah, because we want to try to, so I think that could be another research work to understand how you can shift the beam without influencing the BBU. Because if you do phase shifters, you'll influence the BBU operation.
That is actually my next question. What are the open research gaps in this field?
Yeah, I think I can answer to that. But one of our ideas, but this is still not published, but it's still, we already have a patent. Man, but I don't know if I can talk about it. But just to tell you, one of the ideas was to put, so patch, I think I already told you, patch antennas. So some passive elements on both sides of the main structure of the antenna, okay? And then you have diodes here.
Yeah.
And then you can just, so these patch antennas can like excite this main beam, okay? And make it shift towards one of side or the other by turning on or turning off the diodes.
Is it at all related to massive MIMO and that you have like lots of individual elements that you can control?
Yeah, but those are usually active elements and you need to change the BBU to do that. In here is a simple mechanism.
So it's just, so in this case it's just dotted like intelligent reflective surface, but you just, reconfigurable intelligent surface. You just enable each cell, unit cell at a time, and you just change the phase based on your diode signal, basically. Controlling the voltage to the diode changes the phase.
One final thing to say about this cell sweeping is that it might seem similar to the concept of beam forming or beam steering.
Yes.
But it actually has a lot of differences. Because beam forming also relies on, and beam steering also relies on modeling the beam or modifying the beam so we can shift it towards the user, or we can make it wider, the beam wider or sharper to improve coverage, to improve capacity. It's a very good technology, but it's a very complex technology. Because it requires a lot of processing in the BBU, it is channel dependent, it needs user tracking many times. So with cell sweeping, we aim a much simpler deployment. Okay, so it's different. It's a blind sweeping. We don't need to know where the user is. We don't want to do changes in the BBU. We just want to sweep the beam. It could be almost like a radar system where the signal just goes around, and we just need to serve the users when the center of the sector is pointing into their direction. Okay. So this is important to say that the difference. So it means that, for example, while beam forming is mostly being deployed in millimeter waves or high frequency, cell sweeping could be deployed in any frequency, in any technology, even probably in different wireless technologies besides the cellular systems.